Hello and welcome to the 7th lecture of Machine Learning for Robotics and Computer Vision. In this lecture we are starting with the second block of the lecture, where we are starting to talk about convolutional neural networks for computer vision tasks and robotics tasks. And before we start to dive into this topic, I want to give a little recap of what happened before. So in the last lecture we talked about more traditional approaches to solve certain computer vision tasks like object detection and image classification. And we looked on the ways how to apply the machine learning models in for the specific tasks. And the main thing that people did to get machine learning methods working on the image classification or the object detection was the designing of clever features that enabled the machine learning approach to do the task. So the main deal of the approaches there was getting more complex, more descriptive features that can be then used for the machine learning approach. So this has much to do with the so-called feature engineering. So for the applications on a computer vision task, we had to extract features, and using these extracted features, we are then having our machine learning approach, a classifier that uses these features to do the task that we want to solve in the end. And much of this, or most innovation that happened there, were basically on designing more task-specific and better features, so the feature engineering in the end. And this was the defining thing that came before the convolutional neural networks and the deep learning parts that we are talking now about this. But you remember also we talked a little bit about ImageNet in the last time and about the progress on ImageNet. So as you can see, in 2010 there we reached a top 5 error rate. You remember we are not using just the best prediction, but looked at the 5 best predictions to figure out if this classifier did the right job. And when we looked at this, we get something around, so the best approach reached something like 28.2% error rate. So that means 28% were wrongly classified by the approach. In 2011 we saw a little bit progress on this, and the error rate reduced to 25.8%. And when we now look further, we see the following, that we have in the upper part the more traditional approaches here, and we have one approach that stood out in 2012. And this outlier improved dramatically over the other approaches, the error rate, and reached in the end something like 16.4% error rate. And this is really remarkable because it's such a large gap to the more traditional approaches, like using Fisher vectors or back of words or something like this, that people got recognized, there's something dramatically happening here, and something to look out. And this specifically was the start of the so-called deep learning revolution. So convolutional neural networks, so this specific method was based on convolutional neural networks, as we will discuss now further. And convolutional neural networks showed promising results already on smaller data sets or very specific tasks like digit classification from handwritten digits, like on the MNIST dataset, but also on traffic sign classification. So earlier convolutional neural networks proved already that they can get very, very good results on this task. But as you see, these images are very small, very specific, a very specific task, and therefore, now having something that actually works on larger images crawled from the internet with 1,000 classes and trained there successfully to reach some result in the end was really a game changer in the end. So the success on the ImageNet showed the prospect of convolutional neural networks and also the prospect for more complex tasks. So therefore people recognize this. So the question that you can now ask yourself is maybe, but why are now CNNs happening? And the thing is, why got CNN successful now? Well, there are several reasons, or reasons that I think are mainly the reasons why it was possible. So the first reason was, of course, the availability of data. So because usually convolutional network have a lot of parameters involved, as we will also see later. And training this many parameters needs, of course, a lot of data. So that was the defining thing that we also discussed in the first part of the lecture. So the more parameters you have, the more data you need basically to learn something from, to fix these parameters. Otherwise, you will have something that just overfits to the training data and will never get something good on unseen data in the end. So the availability of the ImageNet dataset was a defining factor. But the other part that also played into the hands of the development of CNNs was the availability of the compute. So before, everything was running on just the CPUs in a non-parallelized manner, and now the availability of the GPUs that made it possible to execute certain things like matrix multiplication or something like this in a parallel fashion enabled to train these networks in a very efficient way, and also in a way that not takes forever. So, and therefore the second part that changed dramatically was the availability of compute. And this was specifically enabled by the graphics processing units, so the GPUs, which were originally meant only to produce pixels on the screen and give nice graphics in the end, but they can basically repurpose to do some scientific computing like matrix multiplications or something like this in a very highly parallel fashion and very fast. And the larger the matrices gets, the better for the GPUs, because they have a lot of shader units that can then be used to compute stuff in parallel. And this was very, very well fitted basically also for the convolutional neural networks. And the third part that sometimes is a little bit forgotten is that the availability of code, and that you had code available that you can use to train these things or to just execute it and download it, and was also something that enabled a lot of progress. And the other part was not only that code is available, so researchers now usually when you have a paper available also provide code with the paper that you can just download and then train the exact same network for yourself, or even have pre-trained models available, is something which was basically for most of the approaches before not happening. So this sharing of the code, enabling reproducibility, was always a little bit painful. So you read a cool paper, but then you had to start from scratch basically to implement it. And this was basically also the advantage maybe of bigger labs, because they had the code from before available, and then you can build up on this. And then this, even for the first, in 2012, there were already some GPU code available that people just could download from the authors page, and then, use this knowledge basically to start from there. And from there, many researchers or many groups then also developed their own frameworks to make the compute capabilities of the GPU available for the user. And these frameworks made it easier to build and train networks in the end. And there are something like Caffe, Theano, Torch, and so on. So, and this deep learning frameworks is a very specific thing that is also enabling now a lot of progress. And there, to mention, are the biggest players basically in this for this frameworks are basically TensorFlow, but also PyTorch. And the thing is there, the libraries implement all the operations that are needed to train and do something with the neural networks in a way that it's optimized for the GPU, because the GPU works a little bit different from the CPU. So you have to take specific care of how you organize the memory and how you do specific things such that they are utilizing the GPU in a way that it's the best, essentially. And to get the maximum performance out there is really a hard engineering task, and therefore it's much appreciated that these frameworks are available. And the deep learning frameworks like TensorFlow and PyTorch are implementing this these basic building blocks that you can then use to train your networks in the end on a GPU in highly parallel fashion, even on multiple GPUs or multiple computers and something like this, distributed computing and so on. So, and in this lecture we are mainly focusing on PyTorch, and so you will also use PyTorch in your homework assignments to implement some parts of the neural networks, but also then maybe in the end some approaches that work directly on the images in the end. And when we are talking about deep learning, we are talking basically about neural networks. So, and in a nutshell, neural network is a composition of functions. And these functions, or this view that you can have on a neural network, is that basically you have a neuron that has some inputs, and for each of these inputs, so here these inputs are called x1 and x2, you have a weight, and then you have the sum over the weight multiplied by the x, plus some bias, so that you add on top of this activation, and this gives you then the activation. And this is the basic building block of a neural network is a neuron. And this neuron is just a linear function in the end. And the specific thing that now you can do is basically you can combine multiple of these neurons together. And each of these multiple neurons gives you then one layer, and this is then a so-called hidden layer because it's using basically the input to compute some values which are then used by the next layer. And you have this layer-wise organization, and each layer basically corresponds to a function. So it's basically first taking this function, on top of this function is basically this function implemented. And when you write it up, you have something like this matrix multiplications here. So the large W is basically just this multiple neurons, and you have your input values x, and then you produce some output, and this is a scalar. And the special thing is now that you are not using just the w's together, because this will not help you very much, because you get again a linear function out in the end when you have this sigma not in there, but you have this nonlinear function in between. So you have first this linear function, and then the nonlinear function applied on this in element-wise fashion, and then you apply the second layer basically, which is just then the W2 on top of this, and this gives you then the output in the end. And in this case, as you can see here, as this is symbolized, is that the neurons take always all inputs into account. So therefore you can talk here about something like a fully connected layer. So this is one fully connected layer that just takes all the inputs that came before and applies a linear transform on it. And usually what you want to have is in the end that you apply some non-linearities in between, and in the end then you have the outputs. And the outputs are then the scores that you can then use for classification. So, and as you can see, or by the naming, you can see already that there's some biological inspiration. So I would call it a loose biological inspiration. So these artificial neurons are basically inspired by the biological neurons that are present in our brain and that transmit information between different synapses. And this is basically some abstraction that you can have, but it's not that simple in the brain. So therefore, neural nets are often wrongly attributed as artificial brains in the end. So they're a simulation of the brain, but this is a disclaimer that you will find in most lectures in the beginning when they are talking about neural networks and convolutional neural networks, that it's maybe inspired, but it's not like the brain. So we are not close to modeling the brain in the way that it works. So therefore, be aware of this, that the neural networks or the convolutional neural networks take maybe some inspiration, but they are much, much simpler than the brain. And we don't know what actually happens all in the brain. So especially when you talk about the size of the networks. They have nothing to do with the amount of, so to say, compute that happens in the brain, and also the specifics that happen in the brain. And a real neuron and the activation of a neuron are much, much more complicated. And there's not only just one-off or some activation function that is in between, but there's a lot of processes happening. I'm not a neuroscientist and also not a biologist, so I cannot tell you exactly what is happening there or what is the difference, but be aware of this. Because usually in the press you will find a lot of hype about, this is actually the next step to reach intelligence. So the things that we are now currently doing with neural networks, or convolutional networks specifically, are amazing. So when you compare it, especially about the stuff that were before there were with the traditional methods, we can do a lot of cool stuff with convolutional neural networks. But they are very specific, but this is nothing to do with intelligence in the end. So they're, the things that you see in the press or whatever are just an overstatement of the capabilities. So we are just basically at the beginning also to go in the direction of intelligence. So that's just a disclaimer, so that you're not walking around and saying like, I'm programming actually brains in the end. But coming back to the neural networks, or to the artificial neural networks, it's like here, this is a common way to represent it with this neuron view, and then you have this hidden layer. And often in the literature you will also have a more building block view, basically, where you have basically here the inputs and the dimension of the inputs. Here in this case is a three-dimensional input, and then you have the layers, and then you see that this layer produces an output of 2, and this produces an output of 3, and so on. So, and this is then, when you have multiple of this fully connected layer, this is then called a multi-layer perceptron. And so this is then a more output-driven way, in a way, to visualize it, and this will also be the way that we are using in the lecture to visualize what are the building blocks of the neural network. So I talked already about that we have some nonlinear function in between that is used to make also the whole neural network a nonlinear function. And now I will tell you something about what are these functions. In the simplest case, or in the case before 2012, often the sigmoid function is used, but also the tanh, which have this shape, which goes here from 0, then at around 0 input it goes up, and then it reaches 1 in the end. And this is going from -1 to 1. And the more modern methods are then using something like this simple function here, the rectified linear unit, which is just the maximum of 0 and x. So that means for all x is smaller than 0, it's just 0. And for this is just a linear function. And this is just enough to have the capability to build very interesting nonlinear functions in the end of the neural network. People, of course, played around with this, and one example of this is the leaky ReLU, which has then a little slope here, which also enables it not to just have 0 in the end here, but a little, it gives it a little bit freedom. But we will look at more activation functions and maybe more specific activation functions later in the lecture. But just to give you an idea of what's happening there. So in most cases, the rectified linear unit is the standard thing that people use, and which also works quite good in the end. Coming back to this example with the fully connected layers, when we now want to apply this, for instance, for image classification, then we have something like this here. We have to first make from our image a large vector. In this case, this is an image of 32 by 32, and of course 3 color values. So therefore we have in the end a large vector of 3072 values, and then we use just fully connected layers to reduce it then maybe in the end, because this is an example here from the CIFAR 10 dataset, where we want to have 10 classes in the end. And what usually is done is not to directly put out the classes here, but have the activations that are then used with the softmax in the end to get then the probabilities out. And in the case of the cipher 10, you have then airplane or automobile and so on. And in the best case, when you give in this image, then it will give a high probability for automobile. And so that means the output in the end is usually then the dimension of the number of classes. So just to give you an idea. So in the ImageNet case, basically we want to have in the end 1000 values out, which we then can use with the softmax to get the probabilities for each class. In a short summary, for the fully connected layer, we have now that the fully connected layer takes, in this case here, n values in, gives out a vector of m values, and therefore we need a matrix to make this nonlinear, this linear function, and this is then m times n. And we have, of course, because we have m values that we are giving out, so we need also m biases. And of course, the fully connected layer is also implemented in the PyTorch framework, and there it's called the linear layer because it's just a linear function in the end. And as you can see here, we have the in features, which is basically the n, the out features, which is basically the m. So these are numbers, and then you can even specify if you want to have a bias or not. And this can then be used. But the problem with this approach of just using fully connected layers in the end is that we always have to reduce our image to a vector and then using this vector with fully connected layers. First, one problem is of course that we have very big matrices here. So if we want to do something interesting, maybe using multiple layers and many layers, in the end we will run into a problem with the number of parameters that we have in the end. And converting basically the image always to a large vector, we are giving up a lot of the structural information about the images in the end. And what we usually want to achieve is, or what is the inductive bias, is basically that when we look a small part of the image, then the neighborhood information about this pixel is telling us something about what's happening there. So, and therefore we want to induce the bias that for getting the information about one pixel, we have to look basically only in the nearer neighborhood. We don't have to look at the whole image basically, but we just want to have a small neighborhood. And this is exactly the thing that we are doing in convolutional neural networks. Coming now to convolutional neural networks, a little bit of history. So convolutional neural networks, generally neural networks, are around for a long time. So therefore it's somehow also surprising that just in 2012 people just recognized, okay, that this is something that we want to have in the end, and this is giving us amazing results. But as I said, data, compute, and everything played into the hands of this. So, and even in 1980, the neocognitron by Fukushima basically had already all the structure there. So the thing there was that it had the structure or the inspiration also from biology to take this small neighborhoods into account, so by using convolutions, but it was not, it was only heuristically trained. So it was not really a really clever way to train it. But basically, as you can see here, it has much to do with what you will see later, also with the development of the convolutional neural networks. So, and then in 1986, the backpropagation, or the practical way to train a neural network, was proposed and to compute the gradients that you need in the end, which we will also cover then in the next lecture, how to do this exactly, was basically a very big step forward to actually train these networks. And using then backpropagation together with the idea of convolutional neural networks then gave basically some amazing results on this handwritten digit task. And this was then also commercially used to identify handwritten digits on checks and post them. This was basically this MNIST example. So as you can see here, the structure is very similar to this thing in the 80s and has maybe some different visualization, but it actually is essentially it's very similar to this. So CNNs are quite some time around. So, and when we have now the building blocks of CNNs, then this is basically the visualization that you have now for the 2012 entry on the ImageNet dataset from Krzyzewski. And this is basically the convolutional network. As I said, it's more tensor-based visualization. So we have here the different layers and the size of the tensors that come out. But we now talk a little bit more about this. So, but essentially, a convolutional neural network has now convolutional layers, the max pooling operations in between, and then the fully connected layers that we already had. So here in the end, these are the fully connected layers. Here these blocks correspond to the convolutions. And in between, you have here the max pooling operations that are not explicitly visualized here, but we will talk about this in more depth in a short time. But first of all, we have to talk a little bit about convolution. So the first part of the convolutional network is basically the convolution. And as you might remember from MSR1 or the photogrammetry lectures on, applying the convolution is based here on these pixels. So we have here these pixels. And what the convolution does is that we have a kernel and we apply this on a certain part of the image. And the thing, so this is a convolution, but usually it doesn't matter if the kernel is flipped or not. So therefore we are just using the correlation. So that we have here a plus, and most frameworks also use the cross correlation instead of the convolution because it doesn't make so much difference in the end. But when we now have the kernel, that is a 3x3 kernel with these entries, we are just sliding this kernel over the pixels here. So that means we are applying this window on the image pixels here, and then we multiply -1 by the 176, 0, and so on and so on. So just applying this to this, the sum over all these values, then we get out -77 in this case. Then we go on, the convolution moves one step further, and then we're getting out this value, and so on and so on. This is basically how the convolution works in the end. So, and now, instead of having the specific numbers, what happens now on the convolutional networks is that these specific numbers are just parameters. And usually they are called weights. So therefore I use a W here to symbolize that they are the weights in it. This is the thing that we want to learn in the end. So first part, the convolution is defined by these weights and the size of the kernel and so on and so on. So, and the specific thing now about the convolution is that when we apply it to an image, this convolution is translation equivariant. That means if we shift the image, then the convolution, the result of the convolution will also actually shift. So I just symbolize here the result of the convolution by this image here, which corresponds to the filter that we had before. And then you can see that the activations by shifting the image will also shift. So, and therefore we have the equivariance of the convolution. So this also implies that it basically is not so important where the stuff is happening in the image, but it can extract still some sensible features in the end, even if things move in the image. When we talk about the convolution, as you might have seen before, is when we just apply the convolution, because the filter has a larger size, so it can only start in the upper left corner. We are basically reducing the size of the outcome here, so this feature map. So, and the size of the feature map is basically reduced by the size of the kernel -1. So larger kernels will reduce the size more, and therefore we have to do something if we want to keep the size. And the usual thing that is done is to actually just have added some pixels in the boundary so that we can move basically the window exactly over the first pixel. And this is then the so-called zero padding. So we are just adding zeros in the boundary of the image, and then we retain basically the size of the image. So padding is something that you will often see in the papers applied. Of course, we cannot only use zero padding, we can also have other ideas like reflecting the images out or something like this. But usually zero padding is just fine for us. Another thing is that we don't have to apply the convolutions basically and just at each pixel, so as we did it before, but we can also apply it in a strided fashion. So that means we are applying only maybe every second pixel, the convolution. And then we are of course reducing the size again of the feature map that comes out, but we are having some properties that we can use in the end. So the stride value is also an important parameter of the convolution in the end. And yeah, as I said, stride larger than 1 reduces the size of the feature map. One other thing that people wanted to do with convolution is basically not having the kernel just applied in this fashion, but by having some dilation. So that means we are splitting up the actual where we actually apply the convolution by having a spacing of the elements. So with the stride, we get the convolution applied on different parts of the image and this different strides. In the dilation, we are splitting up basically the elements of the kernel such that they are spaced larger. So and this will give us then also more information about the image in the end. So, but as with the stride, when we are reducing, when we are using a dilation, we are reducing actually also the feature map in the end. And in these examples, I always used now here this single layer image in the end, but usually we have multiple layers. And specifically here in this example, maybe we have a color image. So that means we have actually 3 channels. And what is usually done is that we also increase the size of the convolution in this way. So in the end, we have a 3x3 two-dimensional convolution, but have additional values for the other channels. So the convolution is really shifted over the multidimensional image, but has always the depth of the input data that came before, in this case 3. But important to note is then, of course, this is then giving us only one activation value for this convolution when we shift it over the image. And in this case, to retain the size of the feature map that we get out, we have the zero padding in the end. And now coming to what is actually a convolutional layer in the end. Convolutional layer is then applying just multiple convolutions. So this is the input to the layer. So this might have not only dimension 1, but or only one channel as input, but many channels. And then we are applying the convolutions. And we are applying multiple convolutions in the end. And this gives us then these activation maps and multiple activation maps. In the end, what we get out is that we have as input the number of channels times h times w. The kernels should have the same size as the input channels times k times k. So we're using here just square case, but we can also use asymmetric kernels in the end. And we have C out number of kernels, and this gives us then the tensor that comes out with C out times h times w. And usually when you apply this, you have then also the activation, but I will come to this in a bit. So, and in the summary, so the input size that goes into the convolution or the convolution layer is always having Cn times h times w. So like for a color image, the input number of channels is 3, but it can also be 100, 200, 1000 or something like this. So, and the thing that we are now have to decide is how many filters we apply. This is the number of C-out filters and the kernel size, of course, and depending on the padding and striding, we can come up then with the size of the resulting feature map in the end. And this, of course, depends then on the padding, but also on the dilation rate, the kernel size divided by the stride. Important here to note is now how many parameters we actually have for this layer. So as you remember, for the fully connected layer, it was like the number of input channels times the number of output channels. In this case, it would be here the number of output channels times the number of input channels times k square. And then we have, of course, the number of output channels bias. And for the convolution, usually people use 3x3 convolution or 5x5 convolutions, but also 1x1 convolutions are often used. And yeah, it might now sound not so intuitive why we want to have 1x1 convolutions, but when we are talking about semantic segmentation or something like this, then it will be clear that this has some advantages. For the padding, we usually want to have always that the input size is equal to the output size. Therefore, we are usually just using a padding of k-1 divided by 2. And for strides, we usually have 1 or 2 or something like this. As you have maybe noticed in the slides, I'm now using the so-called channel first notation, so that the channels come always first. But there's also possible to have the channel last. So, and mainly the conventions are here that in PyTorch is always channel first. So, and in TensorFlow we have the channel last convention. So that means before you're applying the convolution in PyTorch, you have to ensure that the channel is in the first position. And usually when you're reading an image, you have then to convert the channel last convention basically to the channel first convention. And there are methods to just swap the dimensions here. And this is here, for instance, this to tensor, which automatically converts from an image library like the Python image library, the PIL images, into a tensor taking care of this. And here in this specific case, the toTensor method also converts the 255 color values into 0 to 1 values in the end. Yeah. So usually we not only want to apply the convolution on a single image, but the same convolution is applied to multiple images. And so you usually have not only here the number of output channels, but also the number of the images that you put in, and this is called the batch. Why we want to have a batch of images will be getting clear in the next lecture when we are talking about learning. But for now, you can take this as information, because when we're now looking at PyTorch, then you will see that we have here the input size is always the batch size times the number of channels times the height and width. And what you get out is then the number of images, the output channels, and yeah, H out and W out. And as I said, it's also written here. It's basically the convolution layer is called convolution layer, but mathematically it's just a cross correlation. And of course, you not only have the convolutions for two-dimensional convolutions, but also for three-dimensional and one-dimensional convolutions. And a rather new thing is basically that you don't have to care about so much what are the input channels, but this can be also inferred from the parameters of the images that you put in. And there's the specific lazyconv2d, which just uses the information by first putting one data point through this network and then initializes the channel numbers accordingly in the end. At least the input channels, because these are always depending on the layer that comes before. And as I said, usually the convolutions are not only applied just so, but also having then the activation in the end. And the activation is here an element-wise activation, so you're applying the ReLU or the softmax the sigmoid in the end for each element of these tensors here. So, but usually this is not represented basically in the visualizations that you have, but it's just assumed or written in the text that usually there comes the rectified linear unit on top of this. And when we have now the image here, we have then multiple convolutions, and when we are talking about the convolutions, we have also to talk about the receptive field. So what is one convolution seeing? And when we have multiple convolutions that are stacked together, then we can talk about how to increase the receptive field. So how does it work? So we have here now 3 convolutions, and this convolution, so the value of this entry in the feature map that comes out from the convolution, is taking into account these input values. And when you now think of it, then you can also now think of which values correspond these values in this map, in this feature map. And this, when you see, it corresponds to this larger field of view here. So this is then the receptive field. Basically, you have this receptive field here. This is then this maybe 3 by 3, but this is then here in one layer further. It's a 9 by 9 view. So deeper layers usually see then more. And what you want to have in the end is, of course, by stacking more layers, that you have in the end also visible more of the image in the end, so that you want to have all the information from the image. And what you can now do to increase the receptive field in the end is to introduce pooling layers in between. Pooling layers are just like convolutions applied in a strided or dilated fashion, and you reduce the size. Pooling layers increase the receptive field and also have the nice property that it makes it possible to have smaller shifts in the images. And a common way is to have max pooling and average pooling. And now an example of the maximum pooling here, where we apply a filter and take the maximum over a kernel. And this corresponds then to, in this example here, we are taking here a 2 by 2 maximum pooling, so the size of the kernel that we apply is 2 by 2. And in this 2 by 2 window, we are taking the maximum. And that means in this example here, the maximum is 14, so the thing that we're putting out in the feature map in the end is 14 here. And we then, because we have stride 2, we are just moving it 2 pixels further and then apply the same here, so that we have here the maximum is 5, so that we are getting out the 5 here. And we can now move on, and as you can see, this reduces effectively the size of this feature map to this half feature map. So we have now here 6 by 4 pixels, and here we have now 3 by 2 pixels in the end. And commonly we want to have maybe non-overlapping windows in the end. And of course, this is also implemented then in PyTorch by having the max pooling operation here, and there's also an average pooling implemented. And to give a summary, we have now here the summary of the pooling layer. And as before, we have the parameters like kernel size, padding, stride, and dilation. And the output is basically the same as before. The important part is that we have for the pooling operations basically 0 parameters that we can adjust. And commonly applied is that we have a kernel size of 2 and the same size for the stride of 2. So that means we have non-overlapping pooling operations in the end. And in specific case for the entry of the 2012 ImageNet entry for the convolutional network, we have overlapping max pooling operations. Now we have discussed all building blocks of convolutional neural networks. So we had the convolutions, the max pooling operations, but also the fully connected layers. We can now move on basically to discuss what actually the AlexNet, so the entry that was so successful in the 2012 ImageNet challenge, what it made specifically here. So first to note is that because of the time and the size of the GPU memory, it was not possible to train the whole network on one single GPU, but the author made great engineering work to make it work basically on two GPUs at the same time. So from the structure, it had 5 convolutions, 3 max pooling and 3 fully connected layers. And here we want now to specifically talk about a single GPU version that is also implemented in PyTorch as AlexNet basically. And here the number of channels changes a little bit, but we can now go over it in more detail. So we have our input image, which has in this case the size 224. And 3 channels, of course, because it's an RGB image. And the first thing that we do is we apply a convolution. So convolutions are now symbolized by this blue bar here. And of course, with every convolution comes also a rectified linear unit on top. And the first thing that Krzyzewski did is to apply a kernel size 11 and a strider 4. So essentially reducing the original image size to a feature map size of 55 by 55. So yeah, that's one thing that I forgot to mention, is that I'm only showing here the height and width because they are just square images. So that means we have always here a tensor of size 64 times 55 times 55. And this is then the feature map that goes into the next part, and the next part was a max pooling operation. And as I said already in the slides on the max pooling, here it was a kernel size of 3 with a stride of 2, so that you had a little overlap between the applications of the max pooling in the end. Then we had a convolutional layer again. So the input dimension or the input channels are 64 and the output channels are 192. And in this case, this was a 5 by 5 convolution and with stride 1 and padding 1. Then we had the max pooling again, a convolutional layer, some convolutional layers again. So these are the 5 convolutional layers. And here in this blocks, there's only a 3 by 3 convolution applied always. And then in the end comes a max pooling operation again, which reduces then the tensor size to 6 by 6. And the number of channels stays, of course, the same. And then comes the flattening operation, which is basically just turning this tensor, which is a 6 by 6 by or 256 by 6 by 6 tensor, into a 9216 dimensional vector. And this 9216 dimensional vector is then put into fully connected layer. And in this fully connected layer comes then out a 4096 dimensional vector, which is then put again in a fully connected layer. And then we have in the end the 1000 classes. So these are then the class scores that we want to have for the ImageNet dataset. So when you now look at this network, then you can come up with the number of parameters. That it's basically 57 million parameters in the end. But the interesting question is, where are actually the 57 million parameters spent in the end? And for this, we are looking again at the structure. Just as a little reminder, for the convolutions, we had the number of parameters is the number of output channels times the number of input channels times the kernel size, because that's how many kernels we apply. And then we have the number of biases, which is in this case we have number of output channels. And for the fully connected layer, we have just the matrix, which is then the input size times the output size, or the other way around, the output size times the input size plus the number of biases in the end. Just as a short reminder. So, and then we now do the computations here for the first convolutional layer, so conv1. This is then, of course, we have 64 channels as output, 3 channels as input, and we have an 11 by 11 kernel, plus the number of output channels is 64. So that means we have here 64 times 3 times 11 times 11 plus 64, giving us 23,000 parameters that we want to learn in the end for the first convolutional layer. The good thing is that the max pooling layers have no parameters at all, so therefore we are not accounting for them. So the convolution, the next convolution is then accordingly, we have 192 channels as output and 64 as input. So this is this part, we have a 5 by 5 convolution, and this is the number of output channels. So we have here 307,000 parameters. And we can then do this for the other convolutions, and then we see that we are roughly now at 2 million parameters. So that means there's a lot of parameters left that we want to have in the end. And now comes this thing. When we now look at the first convolution, the fully convolutional layer, then we have as input 9,216 values or channels, or a vector of 9,216 dimensions, and we want to have out a vector of size 4096. And this means we have here the product of these numbers, and when you do the calculations, then you can figure out that it's alone in this layer we have alone 37 million parameters. And for the other fully convolutional layers, this is of course here we have input 4096 and output also 4096. So that means we have here 60 million parameters, and then the last layer reduces this to 1000. So therefore we only need roughly 4 million parameters. So which gives us in the end, when you sum it up, like 57 million parameters. So that means essentially the most of the parameters that are spent here are spent in the fully convolutional layers. And when you now think about it, how did he came up with this design decision? So I would say most of it was experience, but also some trial and error. So there is no specific design patterns or something like this. So, and as I said, most of the parameters are spent just in the fully convolutional layers, and more modern variants just have certain design patterns that we will see later in the lecture, which you can take as orientation when you want to really design an own convolutional neural network, but also then use only a single fully connected layer in the end. And this is so more of the parameters are then basically spent in the other layers before. And when we are now talking about the ImageNet from 2012 submission, then we have also to talk a little bit about what were the additional parts that were needed to actually attain this performance. One essential part that is always basically used in to some extent is data augmentation. So as in the case of the Dalal and Triggs approach, where we had this horizontal reflections for the Hawk descriptor, we use basically here the same idea. So that shouldn't matter for most of the classes if you do a horizontal flip, that this changes somehow the class in the end. And what was additionally done, so the ImageNet images are a little bit larger, and from this then were basically parts cropped out, like 224 times 224 images. So we had a crop and a mirror, and this gave then basically the augmented images. On top of this, to even make it a little bit more robust, where color variations added. So for this, PCA was applied on the training set to get the principal components, and using the principal components there was a randomness added to get a little bit different images and to make the classifier in the end more robust, but also to prevent the CNN in the end to overfit to the training data. And one specific part that I only want to mention here, which we also cover later a little bit more in detail, is like the part with the dropout. So in the dropout, the idea is basically while training, not all the neurons or all the parameters of the kernels are trained, but only some parameters in the fully connected layers in the end. So in this dropout introduces basically something, a more robustness in the end to the classification, because you can train more robust in the end. For testing, the same strategy was applied of cropping the image, but here some specific cropping was used. It's like this 4 corner crops and then 1 center crop. And then what was also used, so for each of these images we get the classification result in the end. And this was then averaged over these 5 classification results, and then also the mirrored images were used. So in the end, 10 images were run through the convolutional network. Then the classifications that come out from this were averaged to get then the final result. And the thing that we also covered, when you combine multiple differently trained convolutional neural networks in the end, then you get also an improvement in the end. And this was then basically also done. So not only the result of 1 convolutional network was used in the end to get the best performance in the end, but 5 convolutional networks in the end, but trained with different initializations, so that each of the networks is maybe a little bit more certain about some classes than the others, and then maybe can provide some input. But this gave then in the end the result of the 16.4 error rate. When we are now talking about a convolutional network, it's also interesting to talk about what are the convolutional networks learning in the end. And for this you can visualize, at least for the first layers, just the kernels. And as you can see here, the kernels correspond to something that, when you are using basic vision techniques like Sobel filters or something like Gabo filters, then you will recognize that these are something corresponding in the first layer, something to edges and something like this. And here you have some color variations also in the kernels encoded. So the interesting part is here that just by training, putting in an image, having the convolutional layers and then the output, you get in the end kernels that much resemble this what computer vision researchers did years before, thinking about edges and corners and something like this as low-level features in the end. And when you now want to look at the higher layers, what comes out, it's a little bit more complicated, because visualizing just the kernels that you learned will not tell you anything anymore. And there, Zeiler and Fergus came up with an interesting idea of just running an image through the network, and then at this specific layer just reverting basically the convolutions and the max pooling and so on, to get then in the end the activation map out that this kernel or this layer is basically focusing at. And by using this idea, so to passing in images and then looking where the parts in the image where the specific layer or the specific kernels are highly activated, you can visualize basically what the network does internally. And when you do this, then you get this interesting visualizations here. So when you look at the second layer, so in the first layer you saw that it's reacting on edges basically. In the second layer, by aggregating this edge information, you basically get more finer details of the image. So maybe multiple edges here, but also maybe here something like circular patterns and so on and so on. When you then move on to the third layer, you will see that it's then reacting to specific textual information, something like here this textual information, or here this wheels of cars or something like this. So, and this is basically the basic idea of convolutional network. You start with very simple features at the beginning, and the higher you go in the hierarchy of the convolutional layers, because the convolutions are based basically on the convolutions before, you hope that you get out some more general information or more part information about the image. And when you're then moving up, then you may be getting something like this. So you pass in these images here, and then you will see that certain neurons are basically reacting, or certain kernels in the convolutional layer are reacting basically to the dog faces here in this case, or this boundaries and this text and so on. And when you go even further, then it's maybe the location in the image where the part is represented and so on. And you can now imagine that when you now do this, that you get a very high-dimensional, very powerful feature out that you can then use for the classification. And this is the main part. Not having hand-designed features that specifically focus on this, but to learn it from the data by adjusting the weights of the kernels in the end. And this is the deciding, distinguishing fact here, that we have now a way to do end-to-end learning, so-called end-to-end learning. And before we always had the image, then we extracted some features that we came up or learned or something like this, and then on top of this we trained the classifier. So we really had the separation between the feature engineering and the machine learning classifier in the end that uses these features to learn some interesting classifier in the end. And now here this whole pipeline is basically just replaced by a convolutional neural network. And starting with the image, getting through the filters with the convolutions to the label in the end. And this is then the so-called end-to-end. So we're going from one end, the image, to the label on the other side. And this is a very powerful approach, because you're not only learning this part, but you can also learn basically features that are helping you in the end. And this is also the thing that I want to end now the lecture and give a little summary about the lecture. So as I said, the CNNs were a big breakthrough for the ImageNet classification. Basically, all approaches that came afterwards and submitted solutions to the ImageNet competition were basically using convolutional neural networks. And we will also talk about these and where maybe the main design patterns or the main parts that are also nowadays used for solving vision tasks. So, and as I said, the main enabler to have this performance on the ImageNet classification was basically that the data was available and that we had the compute available by using the GPUs. And as I hopefully convinced you that the convolutional networks learn also very strong features and learn this in an end-to-end fashion. And nowadays, most of the machine learning tasks for vision tasks, so like detection, semantic segmentation, panoptic segmentation, such tasks are specifically solved with convolutional networks. And this is also something that we want to cover then in the next lectures in the end. In the next lecture, we will talk about how to actually learn these parameters and what is needed to basically train the parameters. But we will later then also come to which specific architectures or which specific design decisions are commonly used to solve tasks like object detection or image segmentation in the end. As always, a list of references where you can maybe look up further information. And thank you for your attention, and then see you next week.